All right, so the midterm review sheet, I'm just going to get right at it here. We talked about a bit of this in class. So let's go list all these variables here. So V average is average speed or velocity. The unit there is meters per second. T is time. The unit there is always seconds. All right. So average speed, average velocity, distance or displacement over time, or you could solve for displacement using that formula. So over here, V final is final velocity, and that's in meters per second. The initial is initial velocity, again, meters per second. A, that's an important one. A is acceleration. Alright, acceleration is the rate of change of velocity, so you could do meters per second each second, or you could do meters per second squared. Alright, those are the same. So acceleration is how much the velocity is changing by, or the speed is changing by every second. Now these two formulas, you know, V squared formula, sometimes called the timeless. We use that in a problem if we weren't given the time. This is the displacement formula. So extra graphs, diagrams, and notes. Well, we're often given velocity versus time graphs for objects, right? How does the velocity change over time? So, you know, we have some different ones. So I'll just do a little example here. So, alright, let's say the velocity versus time graph looked like that. Well, that means the object is accelerating over the first part of the motion. It's gaining speed, and then it has a constant speed. So this would be acceleration versus time. It would be a constant positive acceleration, and then it would be 0. Position versus time graph, right? When something is accelerating, the position versus time graph is curved, and then it becomes a constant velocity, so then it goes up at a constant rate. Some stuff to know about these graphs, alright? So of this one, the slope of the line is velocity, right? Rise over run, delta x over t, slope of this. If it's curved, it's the slope of the tangent line. Slope of velocity versus time is acceleration, right? Rise over run, delta v over t. Now this one has an extra thing where the area under the curve, the area equals displacement, and that's important. And that could be either 1/2 base times height, or just base times height, depending on what the shape is. So for the triangular part, you would use 1/2 base times height to get the displacement. For the rectangular part, you'd use base times height to get the displacement. Slope of acceleration versus time we don't use, but the area under the curve would be change in velocity. Alright, again, that would be base times height. We only ever have constant or 0 acceleration. We never have cases where the acceleration is changing in this course. Another important thing to note is, you know, problem solving strategies, right? The other thing we did here was we made this organizational table. V initial, V final, V average, acceleration, displacement, and time, right? So, you know, we use this to say, okay, you know, read the problem, fill out the blanks, pick the right equations, right? So at this point, let's go ahead and look at a couple kinematics problems. Then we'll come back to forces and energy. So problem number 1 here, all right, is answer the following questions for the velocity versus time graph shown above. All right, so remember the slope of that line is acceleration. The area under is displacement. So we're probably going to need that. Answer the following questions. Okay, so describe the motion of the object. Well, this is an object at time equals 0, its speed is 0. At time equals 5 seconds, its speed is 30 meters per second. So this is an object that is speeding up. Object, this, I guess I should say shows an object starting from rest. And speeding up. Alright, and that's about all you really have to say there. Determine how far the object travels during the 5 seconds of motion. So now this is where some of the trouble can start. How far? That's delta x. 5 seconds of motion, that's t. We have to be able to read these and identify the given variables. So, there's a couple ways to do this. We could do average velocity times time. We could do the area under the curve. So, area equals delta x. It's a triangle, so it's 1/2 base times height. So delta x equals 1/2 of the base is, this is the base. This is the height. So the base here is 5 seconds. The height is 30 meters per second. So we get a delta x of 75 meters. We also could have said, okay, delta x equals average velocity times time. Well, the average is literally the average of the initial and final, right? So it's the average of 30 and 0. So you literally add them together, divide by 2, multiply by the time, 5 seconds. And look, that's the same as this, just arranged a little bit differently. You also get 75 meters, obviously. All right? Determine the acceleration of the object. Okay, that's A. Well, we said the slope of the line is acceleration, so rise over run, or just which is the basic definition. It's delta V over delta T. So A equals delta V over T. We usually don't put the delta in front of the T. All right, we usually don't put the delta in front of the T. We just leave it delta T. That's always kind of implied. So our change of velocity is plus 30 meters per second. I usually don't write final minus initial. Usually I just say, okay, what is the change? It's either going up or going down, so let's see what we have. And then the time is 5 seconds. So acceleration is positive 6 meters per second, or meters per second squared. That's just also just the slope of this line. Let's look at another kinematics problem. All right, a remote control car goes from 20 meters per second to 15 meters per second over 6 meters. Determine the time it takes a remote control car to go those 6 meters. Use the given organizational table below. So V initial is 20 meters per second. V final is 50 meters per second. Let's go from 20 to 50. If you know both the initial and final, you can take the average. So the average of 20 and 50 is, all right, V average is 20 plus 50 divided by 2, so that's 35 meters per second. The distance is 6.0 meters, that's given. So we're looking for the time. That's our big unknown variable. All right? So I know average velocity and displacement, so check it out. I have displacement equals average velocity times time. That's one of the equations that were given on the front page here, right? Delta x equals average velocity times time. I know what the average velocity is. I know what the displacement is. So at this point, I could plug those in. So 6.0. And I'm not going to put the units in here because I have the units listed up here. I don't want them to get in the way of my solution, 35t. So I solve for t now. So to solve for t, I do divide both sides by 35. All right, that's going to cancel out 6 over 35. I need to get that actual number. All right, I've got a calculator here. So only a fraction of a second, 0.17 seconds it would be. All right, there's your answer, 0.17 seconds. It's moving pretty fast. That's very fast, actually. So, that's what it is. Now it says determine the acceleration of the car. A. Well, we can do any number of things here, but probably the most direct way to do this is just to say acceleration equals change in velocity over time. I could use v squared formula, but this is more direct. So I'm gaining 30 meters per second. How did I do that? Well, I'm going from 20 to 50. 20 to 50 is a gain of 30 meters per second. And I'm doing that in 0.17 seconds. So 30 divided by 0.17 is 176. So I will call it 180 meters per second each second. So that's a big acceleration, but that's okay. Things can accelerate at high rates. All right? So, boat starts from rest and accelerates constantly at a rate of 5 meters per second each second for 6 seconds. All right, how fast is the boat moving after these 6 seconds? So, listen, I gave you the table up here. Let's replicate it down here. The initial, V final, V average, acceleration, displacement, and time. That's a good test taking strategy, right? You sometimes can get, oops, I missed one. So that's supposed to be V average. That should be acceleration, displacement, and time. I was talking while writing and did the wrong thing. So that's a good test taking strategy to look back and say, okay, what can I pull from a previous part of the test? Well, you can pull this from the previous part of the test, that organizational table. And, I wrote the units here, so now if I'm confident in that, I should be confident down here. So that's the acceleration. That's the time. Starts from rest, that means V initial is 0, right? So V initial is 0 meters per second. Acceleration is 5 meters per second. Time is 6.0 seconds. We want to find V final. All right. Well, let's go and look at our equations. V final, we know V initial, we know acceleration, we know time. So I'm looking at this equation. Acceleration equals V final minus V initial over T. All right. So acceleration equals, you could write it as change in velocity, right? Change in velocity over time. I think that actually is a little bit easier in a way, because if we find the change and we know what we started at, we can easily determine what the final state is. So acceleration is 5. I'm not going to put the units in the calculation. I have them listed here. Delta V is unknown, so I'm going to just leave it delta V over the time of 6.0 seconds. I guess I put the units in there. So multiply both sides by 6. You get delta V equals plus 30 meters per second. So therefore, the old since it started at rest, V final is plus 30 meters per second. So there we go. How far does the boat move in these 6 seconds? So that's delta X. All right. So number of ways to do this. I'm going to practice using El Grande in this video just so you can see how it works, right? Same organizational table. I don't need to write anything. I do know the average velocity right now is 15 meters per second. And I could just do average velocity times time. And that is probably the quickest way to go. 0 plus 30 divided by 2. So I will show that. So it's 15 meters per second times 6.0 seconds. It's probably what most of you are going to do there. So 90 meters. But we do have this other fancy formula. Delta X equals 1/2 AT squared plus V not T. Or V initial T, my bad. All right. This is just 0 because initial velocity is 0. Delta X is 1/2 of A, which is 5, T, which is 6 squared. All right, 6 squared is 36. So 0.5 times 5 times 6 squared, that gives us also 90. So this is an OR. You don't have to show both of these, but it's, we practice with El Grande. Let me see here. Any other kinematics in this practice sheet? All right. Now, looking back here, the one thing I could have added to this kinematics review is the v squared equation. We haven't talked about how to use that. I could have used the v squared equation here. I could have said v final squared equals v initial squared plus 2a delta x. Why I would do that, there's no good reason to use it, the v squared equation here, really. You know, v initial is 0, you have 30 squared v final plus 2 times a times delta x, which is 75. So clearly this is the path of most resistance, right? This is not a fun formula to solve, right? 30 squared is 900 equals 150 times a. 900 divided by 150 is 6. A equals 6. So that's clearly not as simple as doing this, but it's just another way you could solve it using v squared equation, timeless equation, all right? So that does it for kinematics review on this review sheet, one-dimensional motion. I'm going to continue on in a second video and talk a bit more about force.